What's their blood pressure going to be? It's going to be low. What's their heart rate going to be? It's going to be high. Because you understand the mechanisms. It doesn't have anything to do with memorization. You have a question, you scratch it.
I have a question.
Yes.
Is there a difference in the mechanism of how you have a patient with high blood pressure that they say is inherited versus lifestyle?
I have no answer to that. Because we don't know what causes high blood pressure. Primary hypertension, that is. Secondary hypertension, obviously. Secondary to something. But primary hypertension, we don't know what causes it. We know it contributes to it. We know things that help make that happen. But we don't actually know the mechanism of action, why it happens like it does. So I can't say, I think the answer is a genetic, environmental, just the way it is, whatever noise you want to make. No idea. 90%, in fact, 90% of people with high blood pressure in the United States have primary hypertension, and it's idiopathic. But we say, if you want to decrease the risk, don't smoke, limit the alcohol, exercise, eat healthy, blah, blah, blah. Keep the cholesterol levels down with something like Lipitor or eating Cheerios. Since I'm talking about water moving, let me give a quick overview of this next thing. Quick overview, I'll talk about it more later on. We have this tissue over here made up of cells. What happens if tissue right here gets damaged? If cell right here gets damaged, what happens? Cells get damaged, tissue gets damaged. What happens? Well, the same thing happens as a person who gets damaged. If a person gets damaged in their house, they slip and fall down the steps. If somebody gets shot, if somebody gets hit by a car, what happens? Mm-hmm. Pick up the cell phone, what do? Call 911. And who shows up? Just you know, which is who? Really? Guy says, guy picks up his cell phone, calls 911, screams into it, help me, I'm dying. I've been shot, I'm dying. Who shows up? Police, fire, EMS, everybody. There you go, that's the word. Everybody shows up. Police show up, and they show up in cars, in trucks, in helicopters, horseback, bikes, Coast Guard if you're near the water, fire trucks, ambulance, neighbors, family members, guy from the Chinese store. Everyone goes from here to this one area. A whole lot of people go from here to this one area. A whole lot of particles go from here to this one area. When this area gets injured, it sends out a 911 call in the form of chemicals. And then, because of that, who comes? Everyone who can help out. All the different types of cells that can help. All the different types of proteins that can help. Everything comes to that area, which means we've increased the amount of particles in this area. We've increased the amount of solid particles, the solutes, that is in this connective tissue area, for instance, in this visual. I don't know what that is. Like I said, I'll show you again later. This is just a quick introduction. Do you know what we call that? There's a word for this. There's a word for when the cells call 911 and everybody shows up. We call that inflammation. Anytime there is cell death that was unexpected, necrosis, anytime there's cell injury, there's inflammation. Because this unscheduled cell death that is happening or potentially happening means somebody called 911. Everybody shows up. Now, of course, when everybody gets there on this scene that we were talking about earlier, we have people who say, well, we don't need the guy from the Chinese store, we don't need the Coast Guard, we do need an ambulance, we might need a couple more cops over here, we don't need neighbors, but we do need the family members, we don't need the cops on horseback. So there's a direction, right? Initially, everybody shows up, and then they sort of narrow it down. The same thing happens with our immune system. You know, we have cells that are specialized for bacteria, we have cells that are specialized for viruses, we have cells that are specialized for fungus, we have cells specialized for parasites. So everybody shows up, then there's a division. But if we create a whole lot of solid particles here, what's coming next?
Water. The water.
Water. We put a whole lot of solid particles, water's going to come. Now, we also have specialized cells in our blood that have to go from this side of the wall to this side of the wall, so they can move down and help the cause. That means we're going to have areas that have to open up a little bit. This is a blood vessel wall. This is where blood travels. Now, blood is made up of almost half of what? Almost half of blood is water. Almost half. And of course, a lot of red blood cells. So if this guy is going to squeeze his big behind through this opening to migrate down through here to where all these solid particles are, what's going to follow him?
Blood.
Water. Water's going to get sucked down in here. And it's going to fill up this space. And of course, since red blood cells are also flexible and even smaller than white blood cells, they're going to get sucked along with it too. Know what we call that?
A bruise.
Swelling, edema, erythema, the redness. They go, where do you think the redness comes from? We suddenly have red pigment. Didn't anybody think, where did that red come from? How do I have red under my skin? Certainly you think of blood, right? You do when you blush, if you blush. Some of you might not blush. Tougher looking guys probably have never blushed. Where do you think the redness comes from? We get red color from, well, here we have a whole lot of fluid getting sucked down in here. We have blood that is just packed full of red blood cells moving through this space. Now the problem is this. The problem is I've created an extra space here. I've created room that wasn't there before. Which means now an area where everything was nice and comfortable, now I have nerves that are getting smashed. And that's going to cause things like numbness, tingling, pain. Now what I could do is I could suck that fluid right out of there. And that's going to stop that, right? And it will. It'll take that pressure off of the nerve, feel better like this. But if this is still signaling, then everybody's still coming to that area, then we're going to have more fluid there, and that's not going to help at all. So instead, what do I want to do? I want to stop the inflammation. Have you ever heard of medications that stop inflammation? Anti-inflammatories. Where do you think the words come from? This is what they do. This is why we use them. Things like corticosteroids. Those are anti-inflammatories. If we want no inflammation, but we don't want to give a steroid, then we can use something called a non-steroidal anti-inflammatory drug. These are the NSAIDs. Does this stuff make sense to you? Making sense is always good. We stop the inflammation. I don't care what part of the body it is. I don't care if it's in the skin. I don't care if we have to inject it into the knee, into the vertebrae. We're going to use a corticosteroid. Stop the inflammation. So when we get to the immune system, I'll go into more detail. Go into that a little bit more. Is that what you want? Do you want more detail?
I have a small question.
Ask a small question.
So, I understand the intent of decreasing inflammation for the purpose of reducing pain and sparing our nerves. Does that mean that we're sending everyone home as far as it's sending out a signal because it wants something, right? It wants help.
Yep.
So are we sending that help home by doing that?
Some of it, absolutely. Yeah.
So you want a certain level of inflammation, but not a lot.
Sounds familiar. Did we talk about this? Or no, we talked about fever,
We talked
right?
about fever.
Oh, look at that. Look how similar, right?
Right.
It's almost like fever and inflammation. Kind of like these things go hand in hand.
Right.
But too much fever is bad, didn't I say that? But we want a little bit? Man, this sounds a lot like that, doesn't it? We want a little bit of
Crazy.
inflammation. Of course we do. But we don't want too much.
That makes sense.
And isn't that awesome when it makes sense? I think so. Makes it that much easier. Because now you don't have to memorize a bunch of stuff that doesn't make sense. You're just doing it to do it. That way you're not just memorizing a bunch of protocols because that's what they told you the protocol is. You're understanding why they do this. Or you'll go to that protocol and say, but this doesn't make sense. If it doesn't make sense, well, then it can't be true. That's what Judge Judy says. So there must be something wrong in that protocol. And that's one of those times you'll see protocols start to change. You'll see them change a little bit more, and change a little bit more, and change a little more. Someone will come along who understands it and says, this doesn't make sense. All right. So absolutely, we want to have some inflammation. We want to have some inflammatory response. Of course we do. We just don't want to overdo it. Probably going to take up way too much time, but here we go. After a while, no more reason for an inflammatory response, right? Once we got it under control, body says, all right, it's fine. We can stop with the 911 call, stop everybody coming here. Nobody goes home. But we had all this water here because of that. So now the water's going to leave. It's going to seep out through the cracks and crevices. What's it going to leave behind? Some of those bigger cells that got sucked down with it. Remember those red blood cells? And those red blood cells are then going to start to break apart. And then it's going to dump out things like stuff you see attached to hemoglobin, like iron. You see the dark colors that happen? And then it turns yellow after a couple of days. All that yellow is unconjugated bilirubin. Bilirubin, of course, is something that is a part of bile. It's obviously a part of the heme molecule. It's also part of bile. That bitter yellow stuff you throw up after you've thrown up everything else. And bilirubin has to go to the liver to get joined up with his friend, to get conjugated, to become useful. If he cannot get conjugated, then he cannot be useful. So the body stores it in places like the skin. That's why when you see people with liver disease or liver failure, their skin is yellow because it cannot conjugate the bilirubin, the transferase, his buddy. They can't conjugate. They can't be joined up. So now we have this extra that is useless. Deposits in the skin, conjunctiva, makes the skin look yellow, makes the whites of the eyes look yellow. This is what we call jaundice or icterus. You've heard of this? That's the same reason why you see someone get punched in the eye. What's it look like shortly after getting punched in the eye? Big and swollen, red. And then after a couple of days, the swelling goes down, but it's still kind of discolored. And then a couple of days after that, it starts looking yellow, and they'll say, oh, it itches. And then somebody will say, oh, that means it's getting better. No. It means just there's a whole lot of unconjugated bilirubin there. Unconjugated bilirubin in the skin irritates the skin and itches it. That's why you see people with liver disease and sort of scratching all the time because of that. What the hell are we? All right. That's osmosis. Filtration. Filtration is also, oh, we aren't even a little bit behind. Well, I thought we were going to be a little bit ahead there, a little bit behind. That's right. Filtration, something that happens in the kidneys. We are moving water and other things across a membrane. We're using force, though, to move it across a membrane. Not energy, we're using force. And in the example of the kidneys, where we're filtering out the force that we're using is blood pressure. And it's pushing things across the membrane. That's what filtration is. We filter out a lot of water, but our bodies reabsorb about 98% of that water before it makes it to the urine stage. Well, it's still considered filtration. Here you can see what would represent something like, I don't know, a glomerulus with some fenestration, some openings, water, and some of these particles getting pushed out. Things that are too large will not get pushed out. Facilitated diffusion, I think they use glucose. Glucose is a decent example, but the reality is we can also see some of this, some of these lipoproteins go in that same way. I'll show a little video on this in just a moment. I have some of the animation that makes, I think, some of this a little bit easier to see. I think so, at least. Facilitated diffusion. Here we're going to have a membrane that has very specific markers that something has to bind to first. See the clathrin pits on the cell. Characteristics include specificity, absolutely. And if there is specificity, then almost by default there's saturation and inhibition and competition. If you have an area that, if you have molecules that are specific, and they are there in order to bind and move, then of course you're going to see saturation issues and the other two as well. Glucose into the cell. Active transport. Active transport means we use energy. We are moving it against its concentration gradient. We're moving it uphill. There was a part in the textbook, I think it was off to the side a little bit, about, it was about concentration gradients and how active transport moves against the concentration gradient. Passive transport moves with the concentration gradient. Please make sure you read a little bit about that. Very important to understand. In order to move against one's concentration gradient, we have to use energy. That's why they say it's like moving, it's moving uphill. Is that it? Page 61. Yeah. So you can imagine moving something uphill requiring more energy. Endocytosis. Endocytosis is when we want to move something into a cell, but not through a transporter. We're not going to move it in through a channel. We're not going to move it in through a gate. We're going to take in something big. There are two types of endocytosis. One is called phagocytosis, which means cell eating, and pinocytosis, or pinocytosis, which means cell drinking. In both cases, the cell reaches out and engulfs a large particle or a large number of small particles and brings it into the cell. Again, I will show you a quick little video on that. Exocytosis is just the opposite. Exocytosis is moving something, well, out of the cell, something large. Active transport pump. Notice right here, ATP. Sodium potassium pump. Every cell in the body has sodium potassium pump. You need to be aware of the sodium potassium pump. We definitely will get into the sodium potassium pump. Here is an example of phagocytosis. This isn't necessarily moving into the cell like on its own accord. The cell's kind of reaching out and grabbing around it. But notice how the cell membrane was once part of the outside of the cell is now part of the inside of this vesicle. The reason for that is because whatever the cell just took in, like in this case a big bacteria, that's okay. In this case a big bacteria, we don't want the bacteria to come in contact with the cytoplasm because that could ruin things inside of the cell, and we don't want that. So it protects it by keeping it engulfed in this vesicle here. Pinocytosis, you can see a whole bunch of little particles all coming in at once. And then here's exocytosis. It's just doing the same thing but in reverse. So it's removing a lot of particles all at once. Cytoplasm is the gel-like fluid that is inside of the cells. A lot of water. Due to their size, we call these little organs and cells organelles. The nucleus is the brain of the cell. This is where all the important information is kept. This is where all the directions are kept. This is where the DNA is kept. The nucleus is the brain of the cell. So once the nucleus dies, that's the first sign of cell death. If you talk to a histologist or if you talk to a cytologist, they will tell you, or hematologist, they will tell you the first sign of cell death is when you see the nucleus die. The nucleus has a double wall membrane, but it does have large openings. That is to allow things to easily move from the cytoplasm into the nucleus or move out, as the case may be, if it's supposed to. All right, we've talked about DNA. We've talked about how it's not just the blueprints. It's the directions for everything. DNA is the directions for everything. So if I have a 3-ring binder full of directions on how to make everything in my body, just like how to make a building like this. But it's not just how to make a building like this, it's also about how to make the bricks that make the building like this. How to make the paint that paints the walls in the building like this. How to make the sandwich in the cafeteria, or the chocolate cake that's being served in the cafeteria in a building like this. All of those directions are in our DNA. That's what our DNA is. And it's not just about, well, it is just about, it's about structure, and it's about physiology. How much of something should be made as well. When should it be made? Which means that includes neurons. Neurons, of course, being the parenchyma of the brain, the functional unit of the brain. And if it includes neurons, that means it includes receptors on neurons. It includes what neurons release, the neurotransmitters. Well, that's what causes us to think what we think, to know what we know, to do what we do. Which means things like our personality are made up of stuff that comes from our directions, comes from our DNA. Not just about what size shoe you're going to wear. There's a lot deeper than that. Now, if somebody were cruel, if they were mean, you have all these beautiful directions on how to make all these wonderful things. You have all these recipes at your house. Somebody wanted to play a trick on you and come over and get a piece of paper with directions on how to build a birdhouse and take that directions of how to build a birdhouse and slip it right in the middle of your chocolate cake recipe, you're gonna have a problem. Beat 3 eggs, add a cup of milk, cup of sugar, hammer the sides together using 3-inch nails. This cake is not gonna come out well at all. In fact, it's gonna be pretty weird. It's probably not gonna do what a cake should do. It's not gonna look like a cake, it's not gonna taste like a cake, it's not gonna do a cake job. This is what happens when a virus comes along and goes inside of the body. Virus goes into a cell, it gets its own directions and slips them into yours. This is what happens when you expose your basal cells, your squamous cells, to too much UV radiation. That UV radiation causes your DNA to, it was called D-dimers, stick together differently, which is the equivalent of changing the pages in your book, or sticking them together, sticking the recipe together, which means when that cell follows the directions of how it's supposed to look and how it's supposed to be made, it's going to get to these weird directions, and it's going to come out looking wrong, and it's not going to do what that cell's supposed to do. What do we call that? When a cell starts to change, we call that cancer. And mutation, that's when we see DNA change. The phenotype is the mutation, is the cell change. But this is cancer. We see cells start to change and they're not right and they're not doing what they're supposed to do. That's cancer. That's why they say things like, oh yeah, this person has HPV. Well, doesn't that increase the risk of cervical cancer? Yeah, how? Well, that's how. Because that virus starts messing with those cells, puts its own directions in. That cell goes to divide, starts to change, to follow the directions, doing exactly what it's supposed to do. Doesn't realize it's part birdhouse, part chocolate layer cake. Doesn't make sense. It doesn't, doesn't have to think about that. So if we mess up the DNA, we mess up the cell. If we mess up the cell, it can't do its job. We don't want to mess up the DNA. Here's a problem I have with this. Chromatin is a material found in the nucleus that contains DNA, right? Chromatin will eventually form chromosomes which carry genes. Do you read these? Chromatin is a material found in the nucleus that contains DNA, and then chromatin will eventually become chromosomes. Here's the thing. Remember I showed you the cookie pen and the little spring inside, and that's a strand of DNA, and we take that and it's all crumpled up like this. It's not stretched out like this. Not when we're going to divide. It's going to take up too much space. It's easier if it all come together, just like this. And we take that, it's like a little stick. It's like a twisty tie stick. And we take that stick of chromatin and twist it together with another stick of chromatin, and another, and another, and another, and another, and another, until we get chromosomes. This is how that works. So DNA is not found inside of a chromosome. I hate when people say that because it's confusing. Because you would not say wood is found inside of a tree. You do not cut a tree in half and then dump the wood out. Right? But that's how it makes it sound. These chromosomes are not, they do not contain DNA. They are DNA. It's just in its condensed form. And then different areas of each of the chromosomes has specific directions for specific things, or at least somewhat specific. And that's what we call genes.
I think you had a question. Do you have a question?
Do you have a question?
I have
Yes.
but you said D-dimer. I was wondering about it because in the hospital when we drove labs and we talked for coagulation test and they check for D-dimer in case like they're suspected for P. So I was just wondering, what does the D dimer, like, what does it indicate? Like, what does it mean? Because you said it has to do with the DNA, so I don't know.
That's just, that, when I say it's in the DNA, I'm talking about the DNA molecule.
Right.
It creates a shift in it.
Is it the same?
I don't think it's the same thing.
Okay.
Yeah, I don't think it's the same kind of a shift that we see in cancer. Yeah. But I'm sure it has something to do with well, maybe not. I don't want to say it has to do with the genes, because of course polyamorism is not so much, right? We see polyamorism simply because clots form. Although it might have to do with the,
Saying 5D dimer indicator.
Yeah.
Suspected, like, it would only give a clue, but it's not going to tell that there's polyamorism. It was just, if the values are higher, like, it might be.
I don't know, I'll have to check.
What it has to do with it.
I don't know how it has to do with that, but I know what you mean. I don't know how it has to do with a pulmonary embolism. Saying, would you see it in erythrocyte sedimentation rate as well? Yeah. Well, I'll read about that later. I may or may not tell you on Monday, because I'll probably forget. But I'll remember when I get home, because now I'm curious. It's a good question. Okay. Things are right, cells grow in an orderly fashion. Sometimes conditions are also trigger changes in the way cells grow. This can lead to too many cells being produced with a lump or tumor being created. Tumors can generally be either benign, slow growing, non-life-threatening, or malignant. Rapid growing, life-threatening, likely to spread to other tissues or metastasize. You know, a benign tumor in the brain, malignant tumor in the brain doesn't make a difference. All brain tumors are bad. If they're growing, they're bad. Because again, we're going to be moving brain tissue, we're going to be displacing brain tissue. This is what we call space-occupying lesion. It's going to grow and grow and grow, and it's going to push the brain out of the way, which means blood vessels supplying the brain are going to get smashed, which means brain is going to get smashed, which means it's going to die. So all brain tumors are bad. Okay. Didn't get near this word I wanted to. Candidiasis, we call thrush.
Babies.
This is not from drinking milk.